Good morning, everyone. So I'm going to talk about our work on using the deep learning method to play text-based games. It's a joint work with my PhD advisor. So the text-based game is the reason that we want to play text-based game is it is actually a very good proxy to some open world, some real-world open problem-solving agents. For example, when people want to solve a problem by talking to each other, so it's very useful. And the way we choose to the game that we choose to play is a single-player game, which means there is no collaboration between agents or agents to humans. And there is a well-crafted dungeon master, which is a computer. It's actually not a human. So basically, you want to talk or type in some actions into the console and to interact with the dungeon master. And our goal here is to get as much a score as we can. It's kind of like a human to play a game. So this work, if anyone know about it, it's actually a very very old game, very popular during the 1980s. And when you open this game, it's kind of like this. So in the head there is a status bar, which is the first one is the location and your score and the number of moves. And in the middle there is the dungeon master's response or some description of the current environment. And the open front door is kind of an action that you can type in. It's a natural language action, so you can interact with the system. And the system will tell you that the door cannot be opened. So this is we call it a master, and we call this an action. So it's a kind of like a master action, alternatively displayed. But we can also treat it as a kind of a dialogue system. So it's kind of like talking to the master. And here we have the website house, and then the action is open the front door, and the master will see the door cannot be opened, and we call this a trajectory, which is boxed by the black line. And so with this trajectory, we can determine the next action. For example, if we want to type in open the mailbox, for example, there is a mailbox there, and the system will reply that opening the mailbox release a leaflet. And again, the larger black box now is another trajectory. So with this larger trajectory, we can type in the next action, and with the new master given here, and so it's kind of a trajectory with a trajectory. So it's the basic setting. So the way we want to we solve this game is we try to adapt the DeepQ network that was introduced by the Google's DeepMind work, when that they want to play Atari games with this with the same framework. But there are some different here. So here we want to encode trajectory and action. Actually, we want to build a function over the trajectory and actions, and the function will give you the number, the Q value. So then we can use the Q value to determine what's the next action to take. So basically, you want to take the maximum the action that can maximize the Q value to play the game. And here is the illustration here. So the left side is the trajectory, and the trajectory is actually the sentence. And then we use some kind of encoder to encode this trajectory into state. The state is like a vector. And then we try to map this state into the action. So it's like the setting. But there is some challenges comparing with Atari games. So the first one is for text-based games, we can only have partial observation. For example, the master could give you a description of the local environment, but the master could also be just a short response to what you have said. For example, you can do this or you can do that. But the Atari game, some video games like Atari games is different. For example, this one is not Atari games, but for Flappy Bird, you can have all the information in one image. For example, if when you want to determine the next action, you can just use this information from this image. And the second challenge is the action space is actually quite large than the normal video games, because here we use natural language sentences. But in order to to better train an agent, we just limit ourselves to use 130 pre-generated actions, but which is still very larger than the Atari games. And here are some possible encoders. For example, you can use hash functions, which means we don't use any kind of language features, or we can use bag of words. And then we can use some better encoders, for example, LSTM or convolutional neural network to explore strong language features. And we can also use any kind of combination of that. For example, we can also use BERT plus convolutional neural network. So this is the LSTM encoder. So we just use the vanilla LSTM encoder to encode this trajectory into the inner states and map the inner states to the actions. Or we can use convolutional neural network as an encoder. For example, we use a convolutional filter with size 3, and then the convolutional filter can strive over 3 tokens at one time and generate one feature, and then continue like that. And we use 3 different convolutional filters, and then we use max pooling, for example, a pooling layer, to extract the features out and map these features into our action list. So it's different encoders. And our experiment is we have the full game, which we play the Zork, and we use 130 actions. And also we simplify our full game into 2 smaller games. The first one is AppQuest. The second one is the TrollQuest. The first one has 11 actions, and the second one has 21 actions, which is smaller. So we just want to test that. And here is some the convolutional neural network and LSTM model sizes. It's actually kind of same size. So the first experiment is we want to choose encoders. We want to see that which encoder is better. And we compare the LSTM encoder, we also compare the convolutional encoder with different polling layers. So this is the experiment on the AppQuest, the simplest one with 11 actions. And the blue curve is the result of the LSTM encoder. And the x-axis is the time, and the y-axis is the score we can get. So we can see that in 3 hours, the LSTM encoder can converge to the optimal result. And this one is the convolutional neural network with the mean pooling layer. So we can say that it converges a little bit faster, but it's not stable than the LSTM one. And this result is the convolutional neural network with the max pooling layer. So this encoder can make this agent converge in less than 1 hour, and it's very stable. So here the difference is so convolutional neural networks is much faster than the LSTM one. For example, in our experiment here, so in the same amount of time, the convolutional neural network can train 175 epochs, while the LSTM one can only train 14 epochs. So which is much faster means that it can to create a better exploration of the game. So this is the now is the experimental result with our the Choquest, the medium one with 21 actions. So again, this is the result with IEEE encoder. We can see that it can barely tune because it only tuned for like 25 bytes in this amount of time. And this one is a convolutional neural network encoder with the mean polling layer. And this one is a convolutional neural network with max polling layer, which is much better than the previous two. And so now we want to know why it is using max polling is better than the others. So for example, if we choose the action go north, we actually can backtrace this the weight to its previous stage. For example, we could say that okay, the first cell in the vector provides the maximum weight to this action, and then we can map the first cell back to the convolutional features, and then we can find out that the 3 token of west of house provides the most weight to our choice. So it's kind of like automatic attention, that when you make this decision, you just focus on this part of tokens. And this is the result that we extracted with our well-trained encoder. And for example, the go north. So the maximum weighted part is the west of the house, and the second one is the west of a white, and the third one is with a board front door, which means that when we make this decision of using the action go north, the encoder is actually pay attention to this 3 part. And also we can continue this process to like when we make the decision of the next action, we can see that the first one is the west of house, and then north of house, and then it's not all here. So it's kind of like automatic attention, and that's why we use the CNN with max polling layer is the best one. And when we apply this method, when we apply this CNN with max polling layer to our full game, we can see that the result is actually not very good. The result is actually even worse than the Choquest because it's actually reasonable, because here we use 130 actions, but for the Choquest we only use 21 actions. So the next step is how we solve this problem with to explore the word relationships. So the first thing is when we use LSTM, the LSTM is actually encode the position features into the encoder, because it can read the tokens one by one. But when we use the convolutional neural network, it actually lacks this information. So we want to add the positional embedding along with the input. So this is our previous result, and when we apply the position embedding, it actually becomes better. And the next thing we want to explore is we want to explore some synthetic relationship, because like if we repeat the previous result of our auto attention, we can say that some of the words are west of house or west of white, and it's not here. So actually the attended tokens is actually very noisy. So we want to use some dependency parser to actually to make a better result. So this is a dependent parser reordering. We have this sentence. There is a small map box here. The dependent parser actually parse this in the sentence into 2 trees, into 1 tree with 2 levels. So we want so now we want, for example, here is the first level and the second level, and we actually want our the convolutional neural network with the microphone layer to focus on the trace instead of those tokens. When we apply this method, we can see that, so this is the previous result. And the yellow one is actually when we apply the syntactic part dependency parser, so it becomes much better. And we can also extract the features like before. For example, here the goal node is actually attended to a tree instead of to attend to some tokens. And here and here. So now it's like focused on this tree instead of the previous one. And again, so this is the result of the second action. And yeah, so this is our work. So here the final recap is the first faster encoders is preferred in deep learning because the faster you can train which means that in the same amount of time you can train more epochs, you can explore the games better. For example, here we use STM versus convolutional neural network. And the second one is utilizing some language features of the trajectories instead of just treat it as like a normal sentence, can make the training much faster and can lead better agents. For example, here we use positional embedding and we use syntactic dependency. So, okay, so and thank you. Question?
Thank you.
Yeah.
Interesting talk. A question I have, you are, I assume, always playing the same game,
yeah.
And isn't there the danger of overfitting when you do it always the same, that it just learns, oh, I have to go north in this sense, but it does not really understand?
Yeah, and actually it could be, because there is a chance that it could be like overestimated, like it is overtrained for this stage. But there is the problem that we can, like for example here, we can try to start from different locations. For example, we can make some replay instead of every time we start from the initial location, we can actually start from different locations to try to avoid this problem. But of course, this kind of games is. It's not like you can train multiple games together, so it could have a chance to be like overfitting. Yeah.
Any other questions?
Thank you. Thank you.
Is the third speaker here? So the second speaker will be giving a talk entitled Solving Strong and Weak 4 in a Row.
Okay, thank you. Good morning, my name is Jos Uiterwijk. I am from Maastricht University. I'm going to talk about a very simple game, 4 in a row, but I will show you that there are some pitfalls in this game, and I will mainly try to convince you how I solved these pitfalls. So, my table of contents, I of course first have to introduce the game very shortly. Then I will show you how I solved strong k in a row, 4 in a row. I will tell you what strong means. Then I will talk about solving weak 4 in a row, which is a kind of different version of the game. And in that case, I was able to completely solve the game. I always will tell what that means. That was not the case for 4 in a row in first instance. And that is due to something that is called the extra set paradox for strong positional games. So I will show you what that means and what the implication for strong 4 in a row is. But then I was able still to solve this game completely using two different algorithms. So it's an algorithmic solution. And I will show that in 2 steps. And as conclusion, I can state that also strong 4 in a row is now completely solved. And maybe I end with some future research topics I want to pursue in the future. So, what is the game? It's a very simple game, I guess. Maybe you know it all. It's a flat game, not the connected 4. So, k in a row is played on a flat, say paper or board. 2 players, conventionally called black and white. Often it's also called X and O, and that immediately reminds you of tic-tac-toe, which is just an instance, a 3 by 3 instance of 3 in a row, which is of course very simple. Rectangular M by N boards, and therefore we often denote these games as M and K games, Mn being the dimension and K the row that you want to achieve. You place 1 stone at a time, black starts, and the first one who gets K in a row, 4 in a row for my presentation, will win the game. And this 4 in a row can be either horizontally, vertically, or diagonally. So, of course, it can happen that no player achieves a win, and then the game is just a draw. So, with these rules, K in a row belongs to some class of a special type of games called strong positional games, and they're also called maker-maker games. Maker-maker denotes that both players try to make a 4 in a row and have the same goal. It's very easy to prove that for every strong positional game, there are always only 2 possible outcomes. Either the first player wins, or it is a draw. It cannot happen that the second player wins the game. That's due to the so-called strategy stealing argument from John Nash, which you can easily show that if the second player would have a winning strategy, then the first player can use that winning strategy to win himself, and that means that the second player can't have a winning strategy. Very easy to prove. So the only thing you have to look at for black is to try to find a win, and for white to find a draw. Okay, my solver is a very simple solver. It's a straightforward alpha-beta solver, depth-first alpha-beta solver. Of course, there are many enhancements to make it feasible, to make it efficient, and mostly I have 2 types of knowledge in my solver. The first type is I have all kind of knowledge rules that find 1 positions early during the search, much quicker than going to the end of the line. And that makes the search much more efficient. Secondly, I have clever strategies, if I may say so, that guarantee that some positions, regardless of what you're going to do, the second player always can keep the draw in that position. They are called pairing strategies. With these incorporations into my program, I started to solve the game. Of course, it's a very simple game at the start, and let me show you some of the results. First of all, this table. I hope it's readable. I have looked at board sizes of 4 by n, with increasing n. I never need to look at 3 by n or 2 by n, whatever, because you can easily show that if one of the dimensions is smaller than k, than the number of stones you should get, then it is always a draw. So for 4 in a row, 4 by 4 is the first one to consider. It's a draw. 4 by 5 is a draw, etc. For the 5x5 it's a draw, but 5x6 is already a win, a very easy win. At the right column you see the number of nodes that was investigated to prove that the result. So 5x6 is a very trivial win. For 4 by n I need at least a board of size 4 by 9 and larger. And then it becomes a win. But it's much more difficult, and I'll show you why. So let's give a small, quick overview of how you can achieve the wins. On the 5 or 6 board, you see the first 2 moves, black plays 1 response, that is the best response. Happens to be the longest resistance. Black plays 3, and that's a threat, because if I have 1, 3, then you threaten to make a so-called open tree. And an open tree is 3 in a line with 2 open ends. And of course, when white leaves that, then black wins at one of the 2 sides. So 1, 3 should be responded. This was responded by 4. Then you make a new open tree threat. White response. In a special way, I should go one back. By 6. Yeah? In fact, and that's the trick, black has 2 threads at the same time, one horizontally and one vertically. But white can respond by the vertical to the vertical thread by 6, which is a thread itself. And now black has to respond with 7. White then responds to the other thread. So he counters both threads in some clever way. Then I continue a little more. 9 is a thread, 10 is a response. 11 is a direct thread, to which there is only 1 response. And now you see, and it's indicated by these lines, my program sees at once that this is a 1 position for black. If he plays at the dot, B1, then white should respond at B2, but then black plays at C2 and has 2 possible ways to win, either at E4 or at C5. And white cannot anything do against it, so black wins. This is an easy win. On 4 in a row, a 4 by n board, 4 in a row on a 4 by 9 board is also a win, but it's more difficult. The main reason being that black has only open 3 threads in a horizontal way. Diagonally and vertically are always only winning sets of size 4, so you can't build an open 3 thread in that direction. That makes it much more difficult. Okay, he still managed to do that at some point, and there, after 60 moves, the program sees a win for black again at the dot, which is a direct threat. Then C3, white has to respond at A3, and then you win at C4, which is 2 direct threats, one at C1 and one at F1. So black still manages to win. That's for the moment strong K in a row, 4 in a row. Let me talk a little about weak positional games. What are weak positional games? It's a kind of different variation of the strong positional games. And in a weak positional game, the goals of 2 players are different. In a strong, the goals are the same. Both players try to be the first to win. White cannot do that. So there is a new kind of games where still white can win, but the goals are different. And the first player's goal is the same, at least more or less the same. He needs the K in a row, but not necessarily as first. Because a K in a row for the second player doesn't count as a win. The second player has a different goal, namely just preventing the first player from winning. So you have 2 players, one tries to win by 4 in a row, and the other tries to prevent that. If he succeeds, he wins. Okay, so often this is called maker-breaker games, in contrast to the maker-maker games, because the first player tries to win by making the goal, and the second player tries to break that, tries to prevent that. Okay, solving that is much more easy. It's very straightforward to solve them, but so far I don't think anyone has looked at this game. So for the 4x(n) boards, already 4x7 wins. You don't need 4x9. 4x7 is enough to win. A 5x5 board is very trivial. You win, and you only need 7 nodes to show that. So the win on a 5x5 board is extremely simple. The first player plays in the middle. The second player plays somewhere. For instance, this is maybe the best, but what is the best? Everything loses. And it now recognizes this loss at once. My program immediately says, okay, this is a lost position for white. Play at the dot. And now you have threads in both directions. And you have to respond to the horizontal thread. Then you play the square above, and you have 2 open tree threads, and the other player can only prevent one of them. And in this case, it doesn't matter that if the second player plays there at B3 after the first thread, that after playing D4, white can respond at B2, which makes a kind of threat, but it is no threat because that's not the goal of the second player. So any 4 in a row for white doesn't count at all. For the 4x(n) boards, 4x7 was enough to win. Now, for the sake of completeness, I show you the win over there. And you see already at this, after 10 moves, it is clear that after longest resistance, black wins the game. So, 4 in a row, the weak 4 in a row is solved easily. And, what is important, it can be proven that a weak positional game is monotone. That means if I win on some boards, say a 5x5 board, then I win on any larger board that contains the 5x5 board by using exactly the same strategy. There's nothing the second player can do against that. So every win on a weak positional game is a monotone win. And that means that in our case, so the wins on 5x5 and 4 and 7 are both monotone, and that means that in fact this game is completely solved. So 4 in a row is completely solved. Now you understand what I mean with complete. However, and that is what many authors don't mention or tend to forget, for 4 in a row in a strong version, this is not the case. And that is due to the extra set paradox. What is that? That says that this property of being a monotone win doesn't hold for strong positional games, at least not necessarily. So that means that strong 4 in a row is not yet completely solved. I know several boards, but I don't know how to cope with this feature of non-monotonicity. So I show you this set paradox as it was stated by Joseph Beck. If the black player, the first player, starts in the right low corner, then he wins easily. In this case, all straight lines of 3 are winning sets. He wins easily. Either the second player must play in the inside of the large triangle or on the outside. If he plays in the inside, the black responds on the upper corner. White has to respond, then he takes the left down corner and has 2 threads and wins. Yeah? However, and if the second player starts at the outer triangle, then black wins in the same way in the inner triangle. However, if I make an extra set, and that is this picture, you see there's one additional set at the inside. If now black would try the same, white responds by the inner dot with the 4 degrees, with the most degrees. And now, after the same trick, if he plays at the upper side, black has to respond in the right middle, but has a thread himself. And you can work it out. This graph is not a win. So, having an extra set shows that this position, which was a win on a smaller graph, turns out to be a draw on a larger graph. That's the extra set paradox. Okay, now let me skip this. I have talked about that. Of course, it would be easiest for people to still think that 4 in a row on rectangular boards would be monotone, but as I said, it's not proven. So let me try to prove it, and I have an algorithmic way. I define so-called rim boards, and a rim board is an n by n board with a rim outside it, around it, and the first player is only allowed to play in the central board, and the second player may also use the rim. And then you can easily prove, if I have a rim that the second player can use at most k minus 1 size around it, and still is not able to win, then the game, so that's an n k, and with 2 parameters k minus 1, k minus 1. If that is still a win, then the original MNK game is also a monotone win. And that is what I want to prove. So let me see. I apply this to the 5 by 6 board with a full rim of 3 around the board. And you see that now for any rim size from 0, 1, 2, up to 3, and 4 is exactly the same, black still wins, and that means that this win is monotone. This didn't work out for the 4 by 9 board. If I have a rim of size 1 already, black doesn't win anymore. Maybe I can try 4 by 10, but it doesn't work. 4 by 11 is even too complex, so this didn't work. And then I had a final step where I modified my program in such a way that black is allowed to respond in the rim, but only on a direct threat, and only when that response by black is not participating in the final win. I have proven that this still guarantees that if this game wins, that the corresponding MNK game is a monotone win. So I did this for 4 by 9 now, and now you see 4 by 9 still doesn't work, but 4 by 10 does work. Yeah? You need a lot of search for that, but you see for all rim sizes up to 4, it is a win for the first player. And that means that 4 by 10 is a monotone win, 4 by 9 is a win, so that means that 4 by 9 is a monotone win. Okay, my conclusions are they are very short. Strong 4 in a row wins on 5 to 6 and 4 by 9. Weak on 5 by 5 and 4 by 7, it's easier. Weak is monotone, and that means it's completely solved. For the strong, I have proven algorithmically that the 5 by 6 and the 4 by 9 are also monotone, and therefore also 4 in a row is completely solved. I have some future research, but I don't think it's that important. So thank you for your attention, and I'm pleased to have any questions.
Any questions?
It's early in the morning.
It's early in the morning. Okay, well, thank you very much. Is the third speaker here? Third speaker. So this talk will be on learning to select mates in evolving non-playable characters.
And then I'll hold up these signs to let you know how much time is remaining.
Okay, good morning everybody. I apologize, it is very early and I am still half asleep, but that is fine, so let's hope this works properly. Okay, I am Don Ashley, and I'm here to talk to you today about learning to select mates in evolving non-playable characters. This is work done in conjunction with Valliappa, Braedy, and Vadim Bulitko. We're all from the University of Alberta. Unfortunately, there's only me here, because Canada is very far away from England, surprisingly. First and foremost, let's go through a bit of background just to make sure we're all on the same page. So, I hope I don't have to spend a lot of time on this slide, but we all know procedural content generation. You want to procedurally generate content for video games. And it's worth remembering that as video games are getting increasingly complicated, with hundreds of people working for several years, this is an increasingly important field of research and increasingly valuable. And there's obviously several notable examples. I'm sure most of you can name a few of them. Things like Minecraft or No Man's Sky have made heavy use of this. What is artificial life? Because our work is sitting at the intersection of these two areas. Artificial life is simulating lifelike systems in computers. This is interesting because a lot of the time these systems are multi-agent, because life is multi-agent, hence our presence in this track here. And unlike typical genetic search, in artificial life, generally you have some sort of fitness function implicit in the environment. So you don't get to decide whether agents live or die, they just happen to die magically because the world decides to kill them off. And how are these two things intricately related? Well, with computer games, you're also often trying to, somewhere in that game, simulate a lifelike system. One obvious example you can imagine is if we have sort of communities of NPCs with sort of complicated interactions occurring between them, this is a lifelike system. If you wanted to sort of scale up these communities of NPCs to the point where we can reach things which are actually to some like satisfiable way lifelike, you have to do something procedurally at that point. Or you have to have a couple of million people spend a couple of 100 years building that actual community for you, which is probably intractable because in 100 years computer games probably won't look like they do right now. Okay, but this is a very broad topic, so we're looking at something much smaller than this topic. We're looking at the problem of mate selection. So when you have these evolving populations of agents, there does have to be some sort of strategy these agents employ to select mates that and therefore produce the next generation. The problem is, with an artificial life, a lot of stuff you would typically do in normal genetic algorithms don't necessarily hold. So you can't necessarily say, you mate with you and you mate with you. Because you can imagine, if we're trying to simulate lifelike systems, I don't know about you, but I certainly didn't get anything from the government telling me who my mate can be. This is a very important problem, though, because when we do have these populations of agents, if you happen to have two very fit agents, and they happen to mate together, there's no reason to believe the offspring actually might be fit. So, for a simple example, let's say we have a couple of NPCs in a video game trying to live in their world, and one of those ones decides to live by robbing everybody, and the other one decides to live by staying really close to the police station so it never really gets in a lot of danger. Well, the offspring might decide to rob everybody really close to the police station, which probably is a bad strategy. I'm not sure, but I feel like that might be not a good idea. And we normally, I just want to make sure I state, we do normally in these situations try to have some sort of population of agents. That's often our objective. One key problem, though, is it's often very difficult to tell what would make two agents compatible. So for this very morbid example, we have these two wonderful sheep here. This one sheep only has a right eye, and this other sheep only has a left eye. And we can ask the question, if these two sheep mated, would the offspring have 0 eyes, 1 eye, or 2 eyes? Because those are 3 very different levels of fitness in the environment. But I'm not a geneticist, and I certainly don't think most geneticists could tell you that either. Okay, so how do we propose to tackle this problem? What do we investigate here? We are looking at the problem taking a very machine learning-like approach to solving a difficult problem, which is to just toss an algorithm at it and let it do it itself, okay? So we're just going to let the agents decide for themselves how they pick their mates. We're going to evolve some sort of strategy to do that, and we're going to analyze if this can increase the efficiency of evolutionary search in these A-life environments. This does have direct connections back to things like games. So, for example, in Darwin's Demons, this very well-cited game in A-life literature. We have sort of a bullet hell style game where you have this little guy who's going and shooting all of these enemies up there, and the enemies are evolving over time, learning how to beat you more and more and more. If the evolutionary search happens to be very slow, then you may end up getting a lot of gray hair or dying before the enemies actually become challenging. And generally, we don't like to imagine spending decades playing a game, something like this for decades. It's quite boring. So how do we answer this question? How do we investigate whether we can evolve these mate selection strategies in A-life and what the sort of effects of that are? So we take a very traditional A-life domain, which is this wolf-sheep predation model, and this is a picture of it. In this domain, you have grass, which is growing over time. The grass gets eaten by sheep. The sheep then, get eaten by wolves. They're not very smart. The sheep can also starve to death, so you have population explosions where they go and eat all of the grass, and then they all die very quickly. And in our simulation, sheep can also, by chance, just die from natural causes. The agents we're interested in the simulation are the sheep. We are modeling them as evolutionary reinforcement learning agents. I don't quite have time to explain reinforcement learning, but if you know reinforcement learning, then evolutionary reinforcement learning is just reinforcement learning with a evolved reward signal. And we are going to specifically look at the expected lifetimes of populations of sheep as a proxy for the efficiency of the evolutionary search. Okay. So, this is reinforcement learning. We have states, we have actions and things like that. For the states or observations or features or whatever you want to call it, we let the sheep know a couple of key important information about the environment. They get to know how much energy they have at a given step, which they can recover by eating grass or lose if they happen to get eaten by wolves or just lose over time naturally. They also know the distance in heading to the nearest sheep, the nearest wolf, and the nearest patch of grass. Because our environment is very small, this is justifiable. They also have this one weird thing here, which if you're trying to read this is difficult to understand, which is the maximum of the last known age of any of its children. And that's very simply, as a sheep is wandering around the world, it might encounter its children, and it can kind of just sort of like take a mental note, my child, I found a child that was really old, so evidently I had some good reproductive success here. This is an incredibly rough estimate, though. And the last thing they have, which is sort of the key thing here, is they have their preference for the nearest sheep. So at every given step, they have some sort of scalar value telling them how much they like the closest sheep to them. This is useful because they have a couple of different actions in the world, and one of their actions is to move forwards. They can sort of turn left and right. They can eat the patch of grass they're currently standing on, or they can mate with that closest sheep that they don't have preference of. And in order to sort of decide between these things, we followed a very standard evolutionary reinforcement learning framework, where we give them an action network that is learned within their time or within their lives, but is also the initialization of that network is evolved over time. They also have an evaluation network that's evolved over generations. This is how you compute rewards in this ERL framework. And the last thing they have is they have this preference network that's evolved over time. Okay, so how does this preference network work? It's very simple. You take the full genome of the nearest sheep, and you pass it through you put it through a linear combination of evolved coefficients, which gives you the scalar value for preference. So it's a very naive thing of having some part of your genome which defines these coefficients, and you get the dot product of those coefficients with that genome, and that gives you scalar value. But, I don't know about you, but when I tend to go on dating websites, which I admit is quite rare, and I look at people's profiles and they say something like, oh, I really like long walks on the beach. That's great. I also like long walks on the beach. But if I was an aquaphobic, that would probably not be quite so wonderful a feature for them to have. So instead of just looking at the pure genome and passing that into our preference network, we also consider passing in sort of metrics of similarity of their genome to our genome. So we look at passing in sort of the element-wise absolute difference of their genome, or the squared difference, which sort of exacerbates differences there. Or just the Euclidean distance between the genomes themselves. So just that single scalar value, it says, how similar are they to me? Okay, so if you do all of this, what are the results? It turns out that you get a couple of interesting things that happened. So, my mouse is not in the way. Okay, so the first thing to note is that when you do this, you do find that populations do live longer. So compared to having no information about the nearest mate or no preference for the nearest mate, having access to this network does actually increase the expected survival time of these populations. This is statistically significant values I'm talking about here. But a couple of other interesting things emerge. So the bottom red line you're looking at here is with the random matings, which just effectively says they have no preference network at all. And the line right next to it is Euclidean distance. So here we're looking at populations that are alive as time goes on. So how many of these populations sort of continue living? And it's interesting to us because I expect Euclidean distance to do the best, actually, because I expect it to be quite easy to learn, but it actually did as bad as random. And we think that this might be because the distance between genomes is likely to be dominated by features that you don't select for evolutionarily. So this metrics don't work, and this is a classic problem in like density-based clustering methods and things like that. Other interesting things is that when we start comparing the genomes, the absolute difference, squared difference, they actually do no better than just passing the genome of the other sheep directly into these networks. And what this sort of suggests, and how we're kind of trying to think about how we can explain this, is that it's likely due to some sort of coevolution occurring. And because our world is small, it's likely that the population of sheep is only following one single survival strategy, so it's unlikely you're going to see as much of this destructive interference. But an important question here we should ask is that, are they actually learning anything meaningful? Are these sheep actually learning something that matters? Well, if we look at some of the long surviving populations, and we start to look at this, the genomes of these sheep effectively are just the scalar values defining the scalar weights in the networks themselves. So the preference network just sort of says how much you care about that single weight. And what we start to see in the long-living populations, they start to favor things that are important for survival. So for example, this first line here in this graph, which I don't have time to go over the whole graph, but this distance to grass to action mate effectively says, when you mate in our simulation, you lose a huge amount of energy and your offspring starts out with very little energy. It's important to be able to recover that energy quickly. Being close to grass gives you a way of recovering that energy. If you're not close to grass, there's a good chance both you and your child will starve to death before you ever reach any food. And what we see is that in the preference network, the sheep are starting to favor other sheep that do actually care about this distance, where it actually is meaningful to them. Okay, but I'm very low on time here. I think I have I have 3 minutes left. So I have 5 minutes left? Okay. Well, this might be a shorter presentation then. But okay, I'll go through the conclusions really slowly. So, first, what are our major takeaways? The first thing is that when we evolve these mate selection strategies, we do actually see it increase the expected survival time of these populations. What that sort of suggests is maybe the problem of how we pair sheep together can just be solved by letting them do it themselves and make that decision completely on their own. Also, we do see that when you do let them sort of pick mates on their own, they do start to favor agents which have meaningful survival traits. So agents that actually do good things that are good for their survival. And sort of an interesting takeaway from this that we had, and interesting for anybody who ever looks at this kind of stuff in the future, is that how you do compare these genomes does matter a lot. I know that when I implemented this, I thought Euclidean distance was going to be the best out of all of them, and I thought this was going to be a solution, and it actually did really, really terribly, and I sort of got quite embarrassed. So that sort of comparison is quite important. Okay, but this is early work. This is still very, very early work, and there's a lot of stuff we want to do in the future. The first thing is that if I take my sort of dating profile example thing where I go online, I look at somebody's profile, well, I don't typically see their whole genome listed there because that would be quite expensive and for someone who knows very little biology, pretty useless to see someone's genome. So it makes, in fact, what I'm seeing is they've selected certain things to talk about themselves, some of which might be true, some of which might be false, but they're talking about very specific things they want to talk about. So it makes a lot more sense to us that rather than just having this preference network that takes the full genome of the agent, we would actually want to let that agent define its own sort of set of things it's going to talk about, which then gets passed into this preference network. And we do have some results on this. It is really hard to analyze it the way we did it. That's why it has not made it into this paper, but there are some interesting results from this we do have. And one cool thing is that if you actually did do something like this, what you're actually doing is you're getting something like emergent communication occurring. There's a few more things we're interested in investigating. The first thing I should say is I did lie to all of you. We don't actually pass in the full genome into the preference network. Because the genome is the scalar weights that define all of these networks, they happen to include the preference network itself, or the weights of the preference network. If you try to feed that directly into the preference network, then the preference network has to have one weight for every weight in the preference network, plus some weights for all of the other networks, which reduces this mathematical dependency, which I'm told by mathematicians doesn't work and doesn't make sense. So we had to exclude that. But there's some ways we could think of overcoming this, like having some sort of compression occurring. Also, we would like to be able to see that if you let the agents actually define how to compare their genomes to other sheep, then what happens, rather than sort of just fixing it as these different ways are the ways you can compare your genome to that of other sheep. And lastly, we are at IEEE CoG. There is a reason we are here, and it is because we actually want to put these into a game and see if you have players now interacting with this evolution, what does that change and how does that change the result of this? But with that, I will be happy to take any questions.
Questions?
Very interesting. I have a question. Do you check if before a sheep is selecting the mate, if they are related or not?
No.
Okay.
This is very dark because the mating is the darkest bits of nature that's completely unconsensual, and there is no checking to see any relatability whatsoever. It is completely free.
Okay. And also, any sheep can mate with any sheep, or is there like male and female?
No, it is also completely like can mate with any sheep. It is very like basic stuff. I have like a lot of other future work I didn't mention here, but.
What were those population sizes?
The size of the population, the number of sheep that actually existed within the populations?
Yeah.
Oh, I can't remember exactly. I think we were seeing in the region of like a couple of hundred sheep to some extent. So the population started out, I think, with, I can't remember exactly, I think it was about 50 or 100 sheep or 200 sheep, somewhere in that range, and then the populations will often explode to several hundred sheep, normally not more than 1,000 before they would end up sort of starving themselves out.
Any other questions?
I wanted to ask if the wolf population is fixed.
The wolf population, I think it was, we didn't really do much learning there, but the wolf population has sort of certain sets of like general guidelines for its existence. So if there are no sheep, if no wolves, when wolves eat sheep, they get energy and they reproduce on a fixed rule of if you have so much energy, you have like a child or whatever. And if the sheep all go extinct, then a new sheep magically appears, or sorry, no, new wolf magically appears in the environment.
And what about the wolf's preferences?
They have no preferences at all. Their mating is entirely just they produce like a new wolf, but they have no genomes or anything like that. So they're like they're more just part of the environment. One of the future works we did want to look into, I think we mentioned it in the paper, is to look at if we actually treat the wolves as similar agents, what we see.
Any other questions? Okay, thank you. Fourth speaker. Is the fifth speaker here? Okay.
You don't want to HDMI, you have USB. Yes. Yeah. Okay, but that plug into the camera. Oh. Yeah, awesome. Let's just do it. Let's do the adapter then, yeah.
All right. Good morning, everyone. My name is Pavlos Androulakakis, and today I'll be presenting some research we did at the University of Cincinnati with Dr. Fuchs, titled The Evolution of Kiting Behavior in a Two-Player Combat Problem. So you kind of got a preview of this at the video session, so I'll go into more details here. So in this research, we focus on a one-dimensional combat problem where we have two players, an attacker and a defender. The attacker can move back and forth on the line in either direction and has limited weapon energy that it has to try and expend as efficiently as possible. And then the defender, you can think of as like a turret or static defense, and it has infinite weapon energy and will constantly fire on the attacker as long as the attacker is within its range. And so the goal of the attacker is to try and inflict as much damage as possible onto the defender while incurring as little damage in return. And so what we want to do is see if we can use an evolutionary algorithm to make a feedback controller that will let the attacker achieve its objective from any of the initial conditions within our state space. So we have to define our states here. So first we have D, which is the distance between the attacker and the defender. And we have the weapon energy, which is how much weapon energy the attacker has remaining. And so that's two states, so we have a two-dimensional state space shown there on the right. So with our two states, we have the corresponding dynamics. The way the distance changes is based on a parameter VA, which is the attacker's speed, and then the control variable U1, which is how the attacker chooses which direction to go in. So in this case, as the attacker moves back and forth distance-wise, we move along the distance dimension of the state space. The weapon energy, on the other hand, is based on a parameter, the fire rate, so how fast you can expend your weapon energy, and then the control variable U2, which is how fast you can fire, or sorry, whether or not you're firing. So 0 is you're not firing, and 1 is you are firing. So as the weapon energy changes, we'll move along the weapon energy dimension of the state space. So here we have our how we're going to structure our closed loop controller. We have two controls here. Our attacker has to choose its motion and its firing. And the way we choose to do our feedback control is just by partitioning the state space into regions of control. So for example, with the motion control, we can define some arbitrary regions like that. And if you're in the blue region, we'll say you move left, and if you're in the yellow region, you move right. For the fire control, we do a similar thing. You can split it up into regions, and if you're in the blue region, you'll hold your fire, and if you're in the yellow region, you'll fire. So the way this will work is wherever your current state falls within the system, so for example, if your state falls at that red dot, you'll implement the state that is current, or the controls that are at your current state. So in this example, since you're in the blue region of the motion control, you'll move left, and if you're in the yellow region of the fire control, you move right. And so as you move around, that's what will decide your control. So in order to evolve this, we need to be able to parameterize it in a way that we can use. So what we want to be able to parameterize is these boundaries, right? So the way we do that is by creating a grid parameterization. So you can represent these as a matrix of values now. So you can see here, when you make it a grid, you don't necessarily get a perfect representation of the boundaries between the regions, but as you increase the resolution of the grid, you can start to get better and better resolution. So in this research, we used a 16 by 16 grid, and you can see the resolution later. So the way this works now is you take your current state, X, and if it falls right there, you would implement the value of that specific cell. So in this case, that's move left. One artifact of this representation is that on the boundaries between move left and move right, they actually push you towards each other. So the move left will push you towards the move right, and then you'll move back and forth. So when you hit that boundary, it actually effectively becomes a don't move control. So you're moving infinitesimally small left and moving right, so you can actually implement a third control that's not included implicitly and actually stand still. And this is actually used in our final evolved controllers. So the evolutionary algorithm we use is pretty basic. We start with our initial population. We simulate the combat scenario, which will give us a fitness. And then we have an ordered population, which we can then pick the elite out of, and then do parent selection, crossing, and mutation to fill the rest of the population. So the first scenario, before we are able to decide how good a player does, we have to evaluate their fitness. So here we have an example on the right. The first equation there, UF, is the fitness of an agent from any given particular initial condition. So, and it's based on two things. First, it's based on the attacker's damage profile. So in this case, we have what would correspond to a ranged attacker. So on the x-axis, we have the distance, and on the y-axis, we have the damage inflicted. So this deals maximum damage at some non-zero distance. And then the defender's damage profile. So in this case, it's a melee unit. It deals maximum damage at 0 distance and with an exponential drop-off. So these can be anything you want. You can design these to test any type of damage profiles you're interested in. But that's just from one initial condition. We're trying to make a feedback controller. So we have to be able to evaluate it from the entire continuum of initial conditions within the state space. So that's what this equation here shows. So notice that it's evaluating at every single state within our admissible state space. And so the optimization problem becomes to maximize this overall utility. And if you can do that, then you have the optimal controller. So you might be able to see the problem with that. If we want to evaluate it from the entire continuum of initial conditions, that's not really feasible. We can't do that. So what we do instead is we evaluate it at a sampled grid, and the way we pick these values is we actually put them at the center of all of our grid cells. And the reason we do this is because now every single one of our grid cells will directly affect our fitness. So if one of them mutates or changes, it will show up in our fitness function at the end. So we kind of pick these on purpose in very convenient locations. So in the end, our approximation of the overall utility is actually a discrete sum that's not actually infinite. So for crossing, we select two parents at random from the previous generation, and then we cross them using a split point method. So we pick two split points somewhere randomly within the state space, and then the child's controller is based on the distance to each of the centers of the grid cells. So here you can see if you're closer to split point 1, you'll get your genes from parent 1. If you're closer to split point 2, you'll get your genes from parent 2. And so you can actually cross parents in a pretty varied way in this fashion. So you can see here we have like a red barrier there between the two parents' genes. Mutations, relatively simple. You step through every single cell. If no mutation happens, you leave it alone. And if a mutation happens, you simply pick a new value for it from the admissible controls for that state space. So if it's a mutation in the motion control, you pick a new motion value. In the fire control, you pick a new fire value. So here's our first scenario. The first one we look at is a melee attacker versus a melee defender. The melee defender is pretty standard. It has a high damage close up with an exponential drop off. But the attacker is a specialized unit that deals much higher damage at close range, but has a faster exponential drop off. So here was in the video yesterday. You can see on the left we have the fitness throughout the generations. The blue dotted or the blue dashed line is the average, and the red is the maximum with the standard deviation around it. And here on the right we have the two controllers as they're evolving throughout the generations. So the motion control actually evolves quicker. You can see it actually looks pretty clean already at generation 1300. And the fire control takes a little bit longer to evolve. You can see that one on the top left there eventually goes away. So that's the best evolved controller in the end. So if we actually run this best evolved controller, you can see the trajectory moving through the state space on those top two plots. And then on the bottom you can see the simulation of the actual combat scenario. So this green line is where the attacker starts to fire. It goes up on top of the defender until it runs out of weapon energy, and then starts to retreat. And then that black line is where it finishes firing. So you can see it keeps firing as it's running away. And then on the left, or on the top two plots, you can see how the control is decided. So here we have the same exact controller, but we're actually going to look at the damage profiles. So you can see it actually holds the attacker at the maximum inflicted damage there. So it holds it right at 0 damage. And on the right, you can see the cumulative damage profile over the course of the simulation. So you can see at first it's taking increasing amounts of damage as it gets closer because it's not firing. But then once it starts firing, it's starting to do more damage onto the defender, and it starts to accumulate all that score. So the next scenario was a ranged attacker versus a melee defender. So we wanted to see if we could evolve a solution now where the attacker goes to its maximum inflicted damage point, which we set at 5.5. And the defender is exactly the same as the previous scenario. So here's the evolution of that. Same general trend. It starts to plateau around generation 300, but slowly increases. And this one evolved very quickly with motion control. And this is where we'll see the boundary come into play between the move left and move right. And then over there on the right we have fire control that takes slightly longer to evolve. They are evolving concurrently. It's just that for some reason it actually finds it easier to evolve the motion control, and then after it gets that settled, then it evolves the fire control completely. And so these ones actually look a little cleaner. So here's that best evolved controller in the combat scenario. So we see it actually holds it at that non-zero distance and fires pretty much all of its energy there, and then starts to retreat. And that column that you can see on the fire control actually now, like since we represent our controllers in the state space, you can almost look at it and see what the strategy is going to be ahead of time. And so on the left, we see that it actually sits at that boundary between move left and move right, and that's what holds it still at the distance of 5.5. And so that control isn't actually included but it's something that it can take advantage of in our controller representation. So here is the same scenario, but with the damage profiles, and you can see it holds the attacker at the maximum difference between the two. It's actually not exactly at the top, and the reason for that is because we can only hold the attacker still at the boundary between these two regions. And since we have a grid parameterization, those boundaries are only in specific spots. So in this case, we, oops. Oh, went the wrong way. There we go. So in this case, it's like slightly to the right of the peak there. So that's because our boundaries doesn't lie at the 5.5. So here we have two, since we have all feedback controllers, we can actually test these from any initial condition. That was the goal of this. So here we have two additional scenarios that we tested in a different initial condition. So here on the left, we have a melee, the best evolved melee solution, and this is actually a retreat strategy. So what happens here is the attacker starts at a relatively close distance, but with a low amount of weapon energy. So in this case, they don't have enough energy to justify an attack. Like if they started going closer, they would take a lot of damage, and they don't have enough weapon energy to inflict enough to justify it. So they just run away while firing all the remaining weapon energy that they have and retreat. And so this solution actually is the same exact controller that implemented the kiting strategy. So it's robust enough now that it's actually able to contain multiple strategies within the representation. And then so on the right, we have another one for the ranged attacker. In this case, we start really close with a decent amount of weapon energy, and the attacker chooses to run away back to that distance, expend all of its weapon energy, and then continue its retreat after it finishes using whatever energy it has left. So in conclusion, we were able to use the evolutionary algorithm to find the solutions to this two-player combat problem. The solutions were complex enough to implement multiple strategies, so you can do it both ranged and melee, and robust enough to do it in both trained and untrained initial conditions. The grid parameterization, while simple, was able to provide a way that we can use the evolutionary algorithm with the state space model. And in the future, we'd like to try and examine more complex controller representation, so neural networks and stuff like that. And hopefully, we also want to see if we can expand this to a mobile defender, so if the defender is also able to run away or approach you to maximize its damage, or multiple attackers, and then scenarios where we have more interesting damage profiles that correspond to maybe things in actual RTS games. So that's all. Thank you.
We have plenty of time for questions. And we don't have any questions.
Hi there, thank you for your talk.
Yeah.
I was just wondering, you mentioned on one of the slides you couldn't quite get to the 5.5 peak because of the nature of the grid. Have you tried doing it with a finer resolution grid or with irregular strips of the grid just to see if you can hone in on those values?
We did not actually try that, but the reason I put it at 5.5 is because previously I had it exactly at one of the boundaries, and it would perfectly match it. And I wanted to see if I moved it off of one of the boundaries, would it be able to pick the closest boundary to it and move the agent to that position. So, but yes, if we had irregular boundaries or boundaries that could move, for example, in the representation, maybe it would evolve those boundaries in positions where it finds it more useful to put that don't move scenario. So yeah, that's a very good point. Yeah.
Any other questions?
And,
Wow. You finished 5 minutes early.
I can show one additional thing if that's all right.
Feel
I have
free.
an extra slide. I was prepared for a lot of questions, but that's okay. So the reason we actually picked the grid is because what we're trying to see is we can solve these problems for the actual true optimal solution. So on the left there is the true optimal solution. This is a different problem that we're currently working on. That's the true optimal solution to this problem. And so that's the trajectory that will come out of it. This problem, you're trying to get behind another agent, so you're trying to loop behind them and hit them in the back. So that's the true optimal. If we simply discretize it, we actually get a path that doesn't really work. So we originally thought if you just discretize the optimal solution, you might get a pretty good answer. That's not the case. If we evolve it, we get what looks pretty nasty over there, but the trajectory that comes out of it is much, much closer to the true optimal. So that's kind of the reason this discretized method was something we were looking at is because it's not as simple as approximating this true optimal boundary. Actually evolving it, you can get some pretty good performing results, even though it doesn't look like you would expect. So that's kind of the reason we were looking at this grid parameterization for now. So, since we had extra time.
So we have 3 minutes or so before the next speaker, assuming the last speaker's here.
Yes. They are.
They are. Well, technically, we can't start until 20 after.
Okay. I mean, I have more videos, but...
Of course, you can get set up. Sure.
Maybe I can ask you a question, maybe why?
Yeah.
Do you want this?
No, I think I can do it now. So I was like, this is a very binary view of like the representation of the environment. So I was wondering if like for the boundary of the two regions, have you looked at any like probabilistic or models?
So you're saying instead of just having controls that are discrete, like move left, move right, you're saying more probabilistic approach? No, we haven't yet, but that's actually certainly possible, and I think that would actually provide a lot of more interesting
Especially also
data.
for the assignment around like the boundaries when you decide on the evolution.
Yeah, so you're saying like between two boundaries, it's probabilistic which one you'll pick between the two? Yeah, that's actually a very good point. It's definitely something that you can accomplish pretty easily with this representation, but yeah, that's definitely a path forward we can try. And you're right, it's not always as simple as two controls. You might have 4 or 5 steps. Yeah. Thanks.
So you actually have about 2 minutes or so before the show.
Sure.
Yes, what connection do you need?
HDMI.
Yeah, so there's...
Yeah.
Sure. Okay, hello everyone. My name is Joshua Sirota. So I'm presenting work today that was actually done by my colleague Everton and my supervisor Vadim. Unfortunately, Everton had some visa issues and so he couldn't come present himself. But I'm going to try to do his work justice. So the paper that I'm presenting is called Deep Variational Autoencoders for NPC Behavior Classification. So this paper is sort of the first step in a longer-term project, and the ultimate goal of this project is that we'd like to be able to procedurally generate NPCs which have surprising and interesting behavior. So I think the motivation for this is kind of natural. I mean, to actually hand script interesting NPCs is an expensive process. You have to think of different interesting behaviors. You have to make sure that these NPCs are consistent with the rules of the game, that they're responsive to players. And so ultimately, to be able to automatically generate these would be very interesting. And one of our inspirations for this project was this game Project Haster by Polymorphic Games. So in Project Haster, they procedurally generate NPCs in response to the player's actions. So there are some difficulties when you're automatically generating NPCs, and as I mentioned, one of those is assurance control. So how can we make sure that these NPCs are consistent with the rules of the game, that they don't introduce bugs, that they're surprising but just in ways that aren't fun? The next is actually generating surprising and interesting behaviors. One problem when we're trying to generate these surprising and interesting behaviors is that there can be a lack of data. You are generating all of these different NPCs with different behaviors, but to actually produce enough that you can find interesting behaviors. And so the first step that we're going to be taking towards this problem is, rather than automatically generating NPCs, we're going to be trying to automatically detect surprising and interesting behavior. And so, like I said, the specific problem that we're addressing with this work is that we're going to try to classify the behavior of procedurally generated NPCs. And so some of our requirements for this is that we'd like to use a machine learning approach. We'd like it to be completely automated, where essentially we're just given a large data set comprised of many different NPCs behaving in different ways and be able to automatically detect interesting, surprising behavior. We assume that we have access to some normal baseline class. We assume that the data is easily observable. In this case, the data is just screenshots. And also, we would like this approach to be robust to mixtures of classes. So even though we assume that we have one data set consisting of primarily normal NPCs to achieve a baseline, we'd like for there to be able to be some pollution of this normal class and that our approach still work. So there's some important relevant work here. Ahmad did some work on automatically detecting gold farmers in MMOs, and they used a supervised approach, which is in contrast to our unsupervised approach. And the approach did work to some extent, but one of the difficulties that they encountered was that there was some mislabeling in the data set. What they believed to be their normal data set actually was polluted with some gold farmers that hadn't been detected. And so it's this challenge that's seen when you use a supervised approach that encouraged us to take an unsupervised approach. This second paper, Learning to Recognize A-Life Behaviors, is the precursor to this work. And essentially it's very similar to what I'll be talking about today, but once again they used a supervised approach with labeled data. And then these next two papers by Meran and Ribeiro, they actually used an unsupervised approach to detect interesting behavior in crowds. But specifically, the interesting behavior that they detected in the first case was when the mean velocity of people within those crowds was higher than normal. And in the second case, it was when the actual shapes of figures in those pictures were different. So say when the normal data was comprised of pedestrians, but then a bicycle rode through or a car drove through. And so they had these very specific definitions of anomalous, whereas we're making no such assumptions. We don't assume that surprising NPCs are moving faster or that they look different or anything like that. So this is the actual model that we'll be using to try to classify interesting behavior. So it's a variational autoencoder. So essentially the idea here is that a variational autoencoder, it has to learn patterns in the data so that it can reconstruct it. And so what we're thinking is that by training this variational autoencoder on a data set comprised of normal NPCs behaving in typical ways, that when it eventually receives as input a screenshot of NPCs behaving in surprising or different ways, that it'll have trouble reconstructing it. And so essentially what we do is, with this autoencoder, we compute X prime, so this reconstruction of a screenshot, and then we compute the loss of that screenshot, the reconstruction loss, which in this case is just mean squared pixel error. And then if the reconstruction loss is greater than some threshold theta, then we define that screenshot as containing anomalous behavior. And if it's less than theta, then it reconstructed well enough, and so we assume that it's normal behavior. And this is probably a good moment for me to note that Throughout this work, since I mentioned it is difficult to describe what is interesting behavior, what is surprising behavior, the approach that we're taking for this work in particular is that we're defining interesting or surprising behavior as any behavior which is anomalous. So just any behavior with reconstruction error higher than this threshold theta. So the actual environment that our NPCs lived in was this artificial life environment. So it's a predator-prey environment consisting of wolves and sheep. So you can see in this first screenshot, the wolves are blue, and there are two different types of sheep, these orange and purple sheep. So previously, one of my colleagues, when working with the simulation, noticed that there were these two kinds of sheep which we hadn't expected. So the orange sheep are what you would expect. They have an affinity for grass, and so they walk around and they eat and they avoid wolves. Whereas he noticed that these purple sheep they don't have an affinity for grass. They actually have a distaste for grass, but somehow they survive. And so what it turns out is that purple sheep, while they don't like grass, they actually like orange sheep. And so they follow orange sheep around. And since eating is automatic, they just follow these other sheep, and despite hating grass, they automatically consume it and survive. And so the reason that we decided to go with this data set for this work is it gives us a very natural anomaly. So usually there are more, we call the first type of sheep leaders. Usually there are more leaders than followers, but sometimes there are, but about 4% of the time there are more followers than leaders. So in this case, we defined anomalous behavior as screenshots where there are more than 50% followers. And this is the actual input to the variational autoencoder. We took out all of the grass so that the autoencoder can't just count pixels, and we also made leaders and followers the same color. So there's no easy way to distinguish between them. And then because we're detecting behaviors, there's this temporal component. So on the left here, you can see that we took these weighted ghost trails. So then one of the questions is we need to select this threshold theta, which we use to define anomalous behavior. And it's sort of detailed how we did this, but essentially what was done was the autoencoder was trained on the normal data set, and then we computed this Q3 term, which is the error level, so we trained the autoencoder, and then computed the error once again over the entire training data set, and then we computed this 75th percentile Q3. So the error level at which 75% of computed errors were beneath this level. And then we used this search discretized by I, and we created a new data set which now contained normal data as well as synthetic anomalies. And by trying these different thetas, we computed the classification error over this new data set and chose the threshold that gave us the best classification level, or best classification accuracy. And the synthetic anomaly that we used for threshold selection was actually one of these, like these pictures on the left, where we just took a normal image, but we scrambled all of the bits, so just random noise. This is the actual model that we used. So it's a variational autoencoder with 8 convolutional layers, 4 fully connected layers, and then 8 transposed convolutional layers for image reconstruction. And so the comparison that we did, essentially the question was, is it actually worth using an unsupervised approach rather than a supervised approach? And so we compared our unsupervised approach to a supervised approach using GoogleNet. But what we did was we intentionally made the task more difficult for our approach. So we took our variational autoencoder and we trained it only on normal data. Whereas for GoogleNet, we trained it on normal data, but also the anomalous data, both of which were labeled. And so this task of detecting anomalous data should be significantly easier for the supervised approach using GoogleNet. But then because we wanted to see how well these approaches could actually detect brand new anomalous data, we created this third data set consisting of just scrambled agents. So neither the supervised nor the unsupervised approach would ever see this third data set before testing time. And so, unsurprisingly, when the agents were tested on the first type of anomalous data, so the one with more followers, the supervised approach did significantly better, which made, as you can see, it achieved a 97% classification accuracy, which makes sense because it was trained on labeled images which contained that data set. But then what we were glad to see was that when we actually introduced this new type of anomalous data consisting of random agents rather than just followers, the performance of the supervised approach fell to about baseline chance. It was completely incapable of dealing with this. Whereas while the unsupervised approach performed worse than it had in the first case, the accuracy still remained well above random chance at 70%. So we think that this actually does suggest that there is some value to using this unsupervised approach, especially when you won't necessarily know what type of anomalous data you'll be running into. Although clearly if you do know exactly the anomalous data you'll be running into, then a supervised approach seems to be just better. And so like I said in the beginning, even though we assume that we have access to this normal class for single normal class for training, we'd like there to be able to be some pollution in that class. So when a developer is generating thousands of NPC behaviors and trying to detect and trying to first train it on normal behavior, we'd like to be able to assume that at least some of that behavior is not normal and have it not ruin the approach. And so what we did was we took our normal data set and we progressively polluted it with anomalous data. And each time we polluted it, we retrained our variational autoencoder to see how much the performance fell when it was actually afterwards classifying normal and anomalous data. And up until about a 3% level of pollution, it actually continued to perform quite well. But then, as you can see, as it hit 5% and 10%, it all sort of fell apart and performance dropped down to baseline chance. So this approach, it turns out, is at least somewhat robust to pollution in the normal class, but only to an extent. So for future work, we would like to actually bring this into and use it with real games. Like we said, we're very interested in Project Castor, and already my colleague is beginning to work on that game. Also, one shortcoming here is that we didn't use, even though we tested this over many trials, each trial involved a randomly initialized autoencoder, but the train validation test split was always the same. And so we'd like to actually randomize the data set each time. And also we'd like to improve the accuracy. I mean, it was 86% in the first case and 70% with a previously unseen anomaly. And we'd like to bring those up higher. We think there's still a lot of room to actually tune the topology of the variational autoencoder. And one of the approaches that we're looking at is an automated neural architecture search. And also we'd like to make the model more robust to anomalies. So to be able to handle a higher level of pollution. Yeah, that's it. Thank you.
Any questions? Oh, well, thank you very much. And that concludes this session of the conference.